Hello everyone. Uh, this video is all about examples on how to compute moment of a force about a point. So I hope that you enjoy watching because there are 9 examples I prepared for this video. So let's have first example. For the 360 Newton force shown, compute its moment about A and about B in two methods. So the direct method by trigonometry and by Varignon's theorem. So this is the figure. So for the direct method first and Varignon's theorem second, let's consider portion CD. So we extend the line of action of 360 so that we can draw the perpendicular distance between the line of action of 360 and 360 Newton force and this distance here. So because the slope of BC is given, we can solve for this angle here, arctan of 3 over 4, and we can solve x1 by similar triangles. So this is also 35 degrees, and let's call this angle theta here. So that uh, the perpendicular distance is distance BC sine of 35 plus theta. So let's call the perpendicular distance as vis-a-vis. Tangent theta for this angle here is theta, that angle, which is the angle here is 3 over 4. So theta equals 36.87 degrees. Then by similar triangles, x sub 1 as to slope 4 equals 1.5 as to 3 equals distance BC or CD, the hypotenuse, as to the hypotenuse of this, which is 5. So x1 is equal to 2 meters and distance CD is equal to 2.5 meters. So from there, we can now compute the direct um, moment about B, which is counterclockwise, obviously. So 360 times 2.5 times sine of 35 degrees plus theta, which is 36.87. So 360 times distance DC 2.5 sine of quantity 35 degrees plus 36.87 degrees. So moment of the force about B is 855.3 Newton counterclockwise. Then let's proceed to the Varignon's theorem approach. So we resolve this into two components. The horizontal is to the left 360 cosine 35, while the vertical component is downward 360 sine of 35. So both of these components produce counterclockwise moment about B. So moment about B is 360 cosine 35 times 1.5 plus 360 sine 35 times 2, which is x1. So computing moment about B is 855.3 Newton meter counterclockwise, which is the same as the first. Next, for direct method of computing moment about A, so let's draw the diagram. So first, let's compute the distance from A to C. And we already found these values. Then this is the perpendicular distance from A. So the moment is 360 times d sub A. And d sub A is equal to distance AC times sine of this total angle here, which consists of this angle, which is 90 minus 35 55 plus this angle here, which can be solved because this distance is 2 minus x2. So let's solve for x2 first by similar triangle. X2 as to 5 equals 3 as to 12. So x sub 2 is equal to 1.25 meters. Then this distance, therefore, horizontal distance between A and C is 0.75, 2 minus x2, so 0.75. So distance AC can now be solved. Square root of 0.75 square plus 3 plus 1.5, 4.5 square. And as I said, this is 55 degrees, 90 minus 35, and this is, let's call that alpha, arctan of 0.75 divided by 4.5. So tangent alpha is 0.75 over 4.5. Alpha, therefore, is 9.462 degrees. So that Distance AC is square root of 0.75 square plus 4.5 square. So distance AC is 4.562 meters. So having found distance AC and alpha, then moment about A is counterclockwise 360 times d sub A, and d sub A is distance AC 4.562 sine of quantity 55 plus alpha. So F times distance A counterclockwise. So it is equal to 360 times 4.562 sine of quantity 55 degrees plus 9.462. So moment of F about A is 1482 Newton meter counterclockwise. Now by Orignon's theorem, these are the components, so both also are counterclockwise about A. So it is 360 cosine of 35 times 4.5 plus 360 sine of 35 times distance 0.75. So we expect that the answer is the same and the sense is the same. So that's the solution for 1. Let's proceed to example 2. 8.2. For the 50 kilonewton force shown below, compute its moment about A in two methods, by direct method using trigonometry and by Varignon's theorem. Then what is the magnitude and the direction of horizontal force producing the same moment about A? So first, by the direct method, so we need to know the distance from this point on the force, line of action of the force, and point A. But before that, let's solve this distance, 2.4 cosine 25, and this vertical distance here is 2.4 sine of 25. Therefore, the horizontal distance between this point and point A is 3.6 minus 2.4 cosine 25. So it will give us a value of 1.425. And we can now find this vertical distance, which is 3.2 plus 2.4 sine of 25. So it is 4.214 meters. So the distance from A to this point is equal to square root of 1.425 square, distance F. 1.425 square plus 4.214 square. And the perpendicular distance of the 50 kilonewton force from A is d sub A, which is equal to d sub F times the sine of this angle, because d sub A is opposite to these angles here. So this angle is equal to this angle, which is arctan of 1.425 over 4.214, plus this angle here, which is equal to this angle here, arctan of 3/4. So that's 90 degrees. Let's call this angle theta in general, where theta is arctan of 1.425 over 4.214 plus arctan of 3 over 4. Distance F is square root of 1.425 square plus 4.214 square. So distance F is 4.448 meters. Then theta is arctan of 1.425 over 4.214 plus arctan of 3 over 4. So take note that this angle is equal to that angle also. So theta is 55.55 degrees. So direct moment therefore is counterclockwise. So if you pull d sub A, it will rotate counterclockwise. So 50 times d sub A, and d sub A is 4.448 sine of 55.55. So 50 times 4.448 sine of 55.55 degrees. And the sense is counterclockwise, 183.4 kilonewton meter counterclockwise. Now for the Varignon's theorem method, which is simpler because we already found the distances, let's resolve 50 into two components. One is 50 times 3 over 5. This is 5. And the other one is 50 times 4 over 5. So 50 times 3 over 5 is 30 kilonewtons horizontal. The vertical is 40 kilonewtons, or 50 times 4 over 5. So both these components are counterclockwise about A. So the moment is 30 times 4.214 counterclockwise plus 40 times 1.425 also counterclockwise. So moment of the force about A is equal to 183.4 kilonewton meter counterclockwise. Then finally, for the horizontal force and the sense applied at this point here at the line, at the point of application of the force, which produces the same moment at A, so it should be to the right so that its sense is counterclockwise. So we equate the moment of 183.4 kilonewton meter counterclockwise to the moment of this horizontal force, which is h times 4.214. So moment about A is 183.4 counterclockwise is equal to h times 4.214. So h is 43.52 kilonewtons rightward. Then next example, 8.3, an improvised pole is pinned at A and requires 1,600 Newton tension force to be exerted in the rope at B by two crews in order to be erected. Calculate the moment of the tension force about point A in Newton meter. So this is the figure, and there are two ways to solve this, but I'll present the direct method. I want you to solve this again using the Varignon's theorem. So this is an equilateral triangle because all sides are equal. This is the rope line. So the tension in the rope line is 1,600 newtons. And the angle here is 24 given. So this angle with the horizontal is also 24. Since the total angle here is 60, so 60 minus 24, so this angle is 36. And we draw a line from point A, moment center, to the line of action of the force perpendicular to it. And from the figure, this distance, perpendicular distance, is 2.4 sine of 36 degrees. So moment therefore is clockwise, 1,600 times d sub A, and d sub A is 2.4 sine of 36. So moment of the force about A is equal to 2257 Newton meter clockwise. Let's proceed to example 4. Calculate the moment of the 250 Newton force on the handle of the monkey wrench about the center of the bolt, solved in two methods, by direct and by Varignon's theorem. So this is the figure. This is a clip from the book by Mariam and Craig of statics. So first, for the direct method, we need to draw a line from this center of the bolt to the point of intersection of the force at the handle. So that distance can be easily computed. Let's express the answer in Newton meter. So square root of 0.2 squared plus 0.03 squared, that distance. Then we extend the line of action of the force and the perpendicular distance from the center of the bolt so that we can form this right triangle. So from the horizontal, because the angle between the vertical and the force here is 250, that's also the angle between the horizontal and this incline here. So this is also 15 degrees, while this angle here is, we will call alpha. So that this perpendicular distance is equal to this distance, which can be computed as square root of 0.2 square plus 0.03 square, cosine of alpha plus 15, or 15 plus alpha. We'll call that d1, and we'll call this the perpendicular distance, d1 cosine of 15 degrees plus alpha. So d1 is square root of 0.2 square plus 0.03 square. So d sub 1 is equal to 0.2022 meters to 4 significant figures. So substitute, because let's solve for alpha first. Arctan of 30 over 200. So alpha is 8.531 degrees. Then moment, direct moment is clockwise. It is equal to 250 times 0.2022 cosine of alpha plus 15 degrees. That's it. The moment of the force is 46.35 Newton meter. So it is clockwise as mentioned. So if you push this moment arm, it will rotate clockwise. For the Varignon's theorem, the horizontal component is 250 sine of 15 degrees, and the vertical component is 200 cosine of 15 degrees. It is not shown. Just note that the horizontal component is 250 sine 15. This is 250 cosine 15. Now, the vertical component is clockwise, same sense as the answer. The horizontal component produces counterclockwise. So we'll make clockwise moment as positive, then counterclockwise negative. So moment about the center of the bolt is 250 cosine of 15, the vertical component, times moment arm 0.2, minus the horizontal component, moment of horizontal component, 250 sine of 15 times 0.03. Okay, compute that. It is 46.36 Newton meter clockwise. So the very small discrepancy is due to rounding off of this distance here. Example 8.5, determine the direction theta, which is from 0 to 180 degrees of the 800 Newton force F, so that F produces, letter A, the maximum moment about point A, then B, no moment about point A, and C, the magnitude and sense of moment in each case. So for maximum moment, and this is the distance from A to B, and B is the point of application of the force. So for moment to be maximum, this distance AB must be the moment arm of the force. That's the greatest moment arm of the force. So therefore, this imaginary line distance AB and the force must be perpendicular. So that if they are perpendicular, the angle theta is 90 degrees minus this angle here, or this angle here. Let's draw the line first. So this 90 minus this angle here, because the force and the distance AB must be perpendicular to each other for maximum moment. So it is 90 minus arctan of this angle, which is 2.4 over 4.5. So distance AB is square root of 4.5 square plus 2.4 square. Distance AB is 5.1 meters. Then theta is arctan of 90 degrees minus arctan of 2.4 minus 4.5. So theta is 61.93 degrees. For part B, for moment about A to be minimum, the force should be directed towards A so that there will be no moment, or the moment arm is 0. So therefore, it is 180 degrees minus arctan of 2.4 over 4.5, because this is the measure of angle theta, and this angle is equal to this angle here. So that's 180 minus this angle, which is arctan of 2.4 over 4.5 for minimum or zero moment. So theta therefore is 151.9 degrees. So for the answer to part C, the maximum moment is with 800 times 5.1, so it is 4,080 Newton meter, and the sense is clockwise. For the minimum moment, of course, it is 0. Proceed to problem 8.6. The 120 Newton force and the 80 Newton force act on the pipe as shown. Determine the combined moment of these forces about point A. Then determine the magnitude and direction of a vertical force applied at C, which produces the same moment. So this is the figure. Then for easy calculation of moment about A, I'll just present one solution, that is by Varignon's theorem. So if we resolve this 120 Newton force into components, we have 120 cosine 65 as horizontal component, and the vertical component 120 sine of 65. Now for these components, both have counterclockwise moment about A, and this 80 Newton force is clockwise. So since there are two counterclockwise components, let's assume that counterclockwise moment is positive. So moment about A, counterclockwise positive, is 120 cosine of 65, the moment arm is 1.2, plus 120 sine 65, the moment arm is 0.8 times 0.8, then minus 80 times 0.7. So moment about A is equal to 91.86 Newton meter counterclockwise, because the result is positive. Then for part B, for the vertical force to have counterclockwise moment about A, it should be downward and vertical. So from the figure, we equate 91.86 counterclockwise to V sub C times 0.3, because that's also counterclockwise. Solving for V sub C, the vertical force at C is 306.2 newtons downward. And example 8.7, a certain force acting at A, which is at 1, 1 meter, has a moment about point B, which is at 2.2, 4 meters of 4.2 45 Newton meter counterclockwise. Its moment about point C at 5 gamma 0 is 80 Newton meter clockwise. So determine its moment about D, which is at negative 2 comma 3 meters in Newton meter. So first, let's plot all these points and let's analyze the direction of the force so that it satisfies the given conditions. So these are the points, and the force is acting at A. For the force at A to produce counter 45 Newton meter counterclockwise, so it should be under B, like that. And if it is directed up to the right, then its moment about C at 5 gamma 0 would be clockwise. Since the moment about C is greater, so its probable inclination will be up to the right, but as long as it is below B. So this is the possible direction of the force. Let's resolve it into x and y components. So we have fx to the right and fy upward. Now for moment about B, which is equal to 45 Newton meter counterclockwise, fx is counterclockwise, then fy is clockwise. So let's consider fx, moment of fx to be positive because it is counterclockwise, and moment of fy as negative. The moment arm of fx is 3 meters as indicated, or it's very obvious in these grids here, and the moment arm of fy is 1. So therefore, 45 Newton meter counterclockwise is equal to fx times 3 counterclockwise minus fy times 1. So fx times 3 minus fy times 1. So 3fx minus fy equals 45. Call that equation 1. For moment of this same force about C, which is clockwise, 80 Newton meter, Fx, the moment arm is 1, is clockwise. Fy, the moment arm is 4, and it is also clockwise. So both are positive. So Fx times 1 plus Fy times 4 equals 80, equation 2. Solving these two equations simultaneously, we get Fx equals 20 newtons and Fy equals 15 newtons. Having found the components of fx and fy, we now take moment about D. So fx is counterclockwise, fy is also counterclockwise. So both are considered positive. So moment about D is fx times 2, the distance is 2, plus fy, the distance is 3. So fx 20 times 2 plus fy 15, moment arm is 3. So moment about D is 85 Newton meter counterclockwise. So that's the answer. So let's proceed to problem 8. Sample 8.8. The cable AB carries a tension of 8 kilonewtons. Determine the moment about point A of this tension as applied to point B of the slender bar. So this is the figure. So to solve for the moment about point A of the tension force, let's solve this distance as 5 cosine of 30, this one. And the vertical distance is 5 sine of 30, which is 2.5. So this is also, from B, we draw horizontal line that is also 5 cosine 30. This angle here is also 30 degrees. Then since this is 2.5, 6.5 minus 2.5 is 4. So that's also 30. That's 4. Then let's call this angle theta. So the total angle here, as long as it will not exceed 90 degrees, would be theta plus 30. So that the perpendicular component of the tension is equal to the tension force 8 kilonewtons times sine of theta plus 30. The horizontal, the other component is along BA, so it passes through A, so it has no moment, if we solve this by the direct approach. So moment about A is tension times sine of theta plus 30, the component perpendicular to BA, times moment arm, which is 5 meters. And that is clockwise. So tangent theta is equal to 4 over 5 cosine 30. So theta is 42.73 degrees. Substitute into this formula here. So moment about A is 8 times sine of quantity 42.73 plus 30 times moment arm 5. So clockwise. Moment about point A is 38.2 kilonewton meter clockwise. Now, if we use the horizontal and vertical components, The horizontal is 8 cosine theta, and the moment arm is 2.5. The vertical component is 8 sine theta, and the moment arm is 5 cosine 30, and both are clockwise. So t cosine theta times 2.5 plus t sine theta times 5 cosine 30, both clockwise. Substitute 8 times cosine of 42.73 times 2.5 plus 8 sine of 42.73 times 25 cosine of 30 degrees. The moment value is the same and the sense is the same. So let's proceed to our last one, 8.8.9. On one corner of a regular pentagon, 18 cm on a side, acts a 150 Newton force and is directed on another corner as shown below. So determine the moment of this force in Newton meter about all corners of the pentagon. So that's the figure, and it acts at A and it passes to A. So moment about A and about C would be 0, and since this line is parallel to DE, because this is a regular pentagon, then the moment about D is the same as moment about E. So let's solve first the interior angle of a pentagon. So there are 5, so 5 times interior angle theta is equal to the sum of interior angles of a triangle is n minus 2 times 180 degrees, in which n is 5. So 5 times theta, the sum of interior angles equals n minus 2, or 5 minus 2 times 180 degrees. So theta is 108 degrees. So knowing that this is 108 degrees and knowing also that this is an isosceles triangle, we draw a line perpendicular to the force, and that line is the line that bisects the angle 108. Half of 108 is 54 degrees. So that's 54 degrees. This is also 54 degrees. And this is the perpendicular distance, which is equal to 0.18, because this is 0.18 times cosine of theta over 2. So that's 0.18. So this distance is 0.18 cosine of theta over 2. So that the moment of the force about B is clockwise. So moment about A equals moment about C is 0, as expected. Moment about B is force times distance B. The force is 150, distance B is 0.18 cosine of 54. Theta over 2 is 54. So 150 times 0.18 cosine of 54. So moment about B is 15.87 Newton meter clockwise. Now let's solve for the distance D. Distance D. Moment D equals moment E as expected. It is equal to 150 times distance D, or distance E, and that is counterclockwise. So considering this triangle here, the angle here is 90 minus theta over 2, or 90 minus 54. So this is 36. And the angle here is interior angle 108 minus 36. So alpha is 90 degrees minus 54. So distance D equals distance E equals 0.18 sine of beta, because it is opposite of beta. So alpha is 90 minus 54, so it is equal to 36, while beta is interior angle theta, 108 minus alpha, 36. So beta is equal to 72. So moment about D equals moment about E equals force 150 times 0.18 sine of beta, and beta is 72. So moment D equals moment E equals 25.68 Newton meter counterclockwise. So thank you for watching, and I hope that these examples will help you improve your statics experience, and wait for my more videos about statics, and I hope that you learn from my lectures. So don't forget to subscribe.